Well, good afternoon, everybody. Thanks for joining the DSIAC webinar and sticking out with us for another quarantine episode of these presentations. I'm going to give a quick overview of DSIAC, and then I'll give the remainder of the time over to Michael Woudenberg for the technical presentation and the content of this webinar. This is Brian Benish. I'm with Defense Systems Information Analysis Center. And just a bit of background about who we are and why we are hosting this webinar. We are a DoD entity that's organizationally under DTIC, the Defense Technical Information Center. If you're not familiar with DTIC, DTIC is essentially the DoD's technical library that holds millions and millions of publications and reports, technical reports that were produced, at least in part, by DoD or government funding. So if you want to look for any particular technical documents as you're doing any research or engineering efforts, that's a great resource and a good place to go. But DTIC's recognize that for those who are doing research and trying to find information, there's a tremendous amount of records, tremendous amount of information out there. It's very difficult to navigate. And so they've stood up these information analysis centers, of which we are one of three, the DS, Defense Systems Information Analysis Center. We have two sister IACs, Information Analysis Centers, HD IAC, Homeland Defense, and CS IAC, Cybersecurity Information Analysis Centers. The distinction between each one of us is going to be defined by our technical focus areas. Defense systems comprised of about 10 now technical focus areas, autonomous systems being one of those, directed energy, advanced materials, energetics. I won't rattle them all off. Then Homeland Defense has their own set of technical focus areas, and cybersecurity theirs as well. But what we do is we're here to help you all, those who are performing research and engineering for the DoD, the defense community at large. We're here to help you find the information you need and kind of get a head start on the work you're doing. What we want to do is help mitigate, eliminate as best we can the redundancy that occurs throughout the DoD community. So if you're getting ready to kick off some sort of new engineering or research effort, we would like you to come to us first and say, hey, has anybody else done this sort of work? What else is out there in this area? And we'll help pull some information together to give you a head start. That head start might consist of related documents and publications that are out there, or it might consist of a bunch of contacts, organizations we know that are doing similar work, and we help facilitate some collaboration there so you can maybe build on whatever work you're planning. A lot of that is conducted under a service I just want to quickly highlight called our Technical Inquiry Research Service. It's a free service that we are fully funded to perform on behalf of anybody doing work in the DoD research and engineering kind of domain. So if you bring your questions to us, asking what else is out there, you need some help getting a head start to your work, we spend about 4 hours of research time from technical folks that are on staff who are able to kind of understand the jargon, terminology, the landscape a bit, and again, compile some information to give you a head start on whatever effort you're working on. So I would encourage you to for more information about that or information on our organization as a whole, go to our website, DSIAC.org, and you can kind of poke around and see what else you might be able to find there. If you have any questions, there's a contact alias. Feel free to shoot a note to that. There's plenty of forms you can fill out, technical inquiry forms, or way to kind of submit your questions. And of course, if you have any particular questions for myself, please feel free to get in touch with me. My email should be somewhere on the website. Again, my name is Brian Benish, and I'd be happy to chat with you more about our organization. But to that end, we to the end of helping to eliminate redundancy and fostering collaboration, we want to highlight and feature work that's being performed kind of in the DoD community, again, in our charter technical focus area. So within the area of autonomous systems, we're happy to have Michael Woudenberg from Lockheed Martin give a presentation on the work that they have been doing, kind of a summary of some of their research efforts, so we can help, again, create an awareness of work that's being done and hopefully spark some interest, spark some collaboration, and see what comes of it. So I'm happy to have Michael here to be delivering this presentation. I will note, as a sort of teaser for you, this presentation is sort of a precursor to a more detailed article that will be published in our forthcoming summer edition of the DSIAC journal. That should be released in about a month or so. So keep your eye open for that. If you're not already a DSIAC member, we'll post it online. If you're a member, you'll get an email notification of when that's published. But again, his article, the article that they produced, will be in that journal as well. So if you have some detailed questions or any questions before that publication comes out, feel free to contact us and we'd be happy to entertain them. But again, just wanted to kind of give you the heads up on that publication. So without further ado, I will hand the presentation over to Michael, although I will make one more quick comment here. The question, so the way we're going to run this webinar, Michael's going to deliver his presentation, and then we will have questions that we'll entertain at the end of the presentation. If you have any questions during the presentation, I would encourage you, when you have questions during the presentation, to submit them. There should be a button at the top of the screen if you're logged in through the web platform where you can submit questions and answers. And we will create a running list of them and address those at the end. So at any time you have a question, put that in the queue for us to address at the end. There is an attendee chat, a presenter chat. I would ask if you use that to just keep that to specifically chats and not to questions. I'll do my best to kind of extract any questions that might get dropped in there, but again, really encourage you to put the questions themselves submitted through the audience Q&A portion that you should be able to find through the top of your screen. So that said, I'm going to go ahead and switch over the presentation here. And I will kick it off to Michael. Still there, Michael?
I am.
All right. Make sure this presentation switches over. All right. Those slides showing up for you?
Yes, it is.
All right. Take it away.
All right. Good afternoon. My name is Michael Wittenberg. I work out of Lockheed Martin in Orlando under the Missiles and Fire Control line of business. Part of a team that was working for quite a few years on frameworks for autonomy. Mark Waltensberger, Jerry Franke, Matt Dorsey, Troy Schiedler, and Kevin Schlosser were the main team members, and supported by a much larger network of Lockheed Martin experts in this field. So what we're going to go over today is kind of the perennial problem that we found with designing for autonomy was getting people to a common language of what we were even talking about, trying to separate the fact from the fiction, trying to balance the buzzwords from the reality, and really trying to develop frameworks by which we could kind of tease out this wicked problem space. And when we look at autonomy, we really do see a kind of a wicked problem space. Just with what I mentioned, just the buzzwords and the reality is one aspect of that, but then the permutations and the complexities that become inherent as you start getting into truly autonomous design. So what we're going to go through today is kind of our path that Lockheed took through reducing this wicked problem space, starting off with the baseline of the conceptualization of autonomy, introducing the analysis frameworks that we've developed that help break down and bracket the space for design, and then looking at solving some of those systems lifecycle design issues. Really, how do we design for autonomy? So starting off with the conceptualization of autonomy. So first off was this need to go from the perspective all the way from customer needs down to enabling technology. One of the challenges that we have faced is a lot of good enabling technology and limited understanding of how it's going to meet the customer need, or customer needs that are being articulated that are challenging as we get down to the enabling technology. And so what we realized in this space was breaking down from the customer need through the systems architecture, then determining the autonomy allowed you to balance enabling technology. And we're going to kind of go through this sequence, this waterfall type activity as we go in. One of the key elements, we'll hit on this again, was that when we defined this, we found out that autonomy was not the leading indicator. It was customer need, systems performance, cost, TTPs, et cetera, then informed by the architecture, at which time autonomy came into play. We'll see a great example of that in just a second. So as the autonomy baseline, Lockheed Martin has identified that an autonomous system is one that composes, selects, and executes decisions with varying levels of human influence. A heuristic that our team came up with, just the way we execute kind of day to day, is that autonomy is a gradient capability enabling the separation of human involvement from systems performance. These are partnered into manned-unmanned teams. We're not ever going to have within the DoD or virtually anywhere an autonomous system by itself, unencumbered by humanity. You're always going to have those teamings, which are supported by autonomous systems, which are supported by those technology enablers, of which some of those technology enablers are things like AI. There's a perennial question that comes out there of, AI or autonomy, and it's like, well, that's a false dichotomy. It's both, but it's what influences along the way. So I can use AI to create improved autonomy, or let's say increasing the separation of human involvement from systems performance to allow more functional manned and unmanned teaming. I'm going to reiterate this one again. Autonomy is an enabler. When I first started on this adventure, it was how do you design autonomous systems? And what we found was when you go out designing autonomous systems, you end up getting very complex systems that are difficult to actually get into use. But when you design for performance, going back to what does the customer need, and then backing it back down. There's a recent project that we worked where it was we needed to create an autonomous wingman. And my goodness, did they find a lot of autonomy that they could stuff into that system. But when we actually broke it back out and said, what are you looking for? Oh, extended sensor range for a classic 4th-gen aircraft. Okay, what do you need to do that? And by the time we stripped it back down, you really didn't need a crazy autonomous system to achieve the actual mission needs. So we went from an autonomous system that was highly complex, almost impossible to V&V, and more than likely not going to meet schedule, scope, or budget, to a system that we could deliver under our normal acquisition processes within 3 to 5 years. So understanding the enabling aspect of that is critical to kind of rethink, are we designing for autonomy, or are we designing for autonomy, or are we using autonomy for our designs? One of the last elements of autonomy that we identified is that autonomy fundamentally exists on, as we found, in 3 dimensions. Systems intelligence, what we might call AI, independent operation, which that would be your separation of systems performance from, or human involvement from systems performance, and then your collaboration. So the X and Y axis work well to describe a single system. But when you start talking manned-unmanned teaming, the 3rd dimension, the Z axis, needs to come in so that you can understand the relationships between this. We'll see an example of this kind of fleshed out with one of our frameworks a little later, but this kind of was derived when we were challenged to model modeling and simulation of autonomy. One of the issues that we've kind of came across right off the bat was when we model humans into a M&S environment, we're actually modeling proxies for humans, meaning we're designing or modeling in something that has a proxy for intelligence, a proxy for independence, and relationships between the two. That was really kind of informative to find out when we were looking at modeling simulation. These 3 dimensions work for both humans, and they work for systems, and they work for MUM-T environments to kind of identify the relationship between them. Next is the layers of autonomy. This is something that I find critically important, is that autonomy is often, this was, I believe, from the Defense Science Board 2012 study, I think, where they identified that too often we focus on the autonomy at the entity level. Think about that as like a self-driving car. Well, the self-driving car becomes complicated because it's an entity and it's encapsulated and it has to work in its own environment. So the next layer that needs to be taken into consideration is the integrated system. What if, let's say in that self-driving car example, if we could break into system road, what would that allow us to be able to do? Hang tight 1 second, I'm getting some chats. Okay, if you cannot see the slides, they are available for download at the DSIAC website. And I am on slide 8 for those of you that are following along in an offline version. So I hope that helps. All right, let me, so entity design, it's complicated. It's what we instantiate, it's what we focus on. It's complicated. If you can get into the integrated system, again, think system road versus system car, and you could have, instead of having to have machine vision and all the algorithms to identify a stop sign, if that stop sign could identify itself, how could you reduce the complexity of both the super system and your entity system? If an intersection could pick up control of vehicles and pass them through versus individual vehicles trying to navigate and negotiate through an intersection, you could actually reduce the complexity of both systems and actually achieve higher performance with, ironically, less autonomy. System security is a third layer. That is probably one. I came from a background previously looking at cybersecurity. Security is so overlooked, and as we start getting into the integrated system, we start collapsing the kill chain, we start communicating between all these assets, the number of additional attack vectors goes through the roof. So another study that I've been working on is looking at that problem twofold. What are the unique security implications for autonomous systems? And then flip it around, what are the opportunities that autonomy or autonomous systems can provide to actually ensure system security? The last layer here is infrastructure. We like to think about applying these things, especially in the DoD, to the entities and the systems that are actually fielded. But we can also apply our lessons learned to all of these design features to our infrastructure. The ability to make products better, faster, and cheaper that are secure, integrated, with balanced levels of autonomy across these layers. So kind of breaking back, we'll recap quick the conceptualization. Autonomy is a gradient capability enabling the separation of human involvement from systems performance. It exists on 3 dimensions: intelligence, independence, and collaboration. It has layers of entity, infrastructure, security, and then your integrated system, and is an enabler. It's not necessarily the leading thing that we should be designing for, because we found over and over in our studies here in our design work at Lockheed Martin that when you start off to design an autonomous system, it gets wicked complicated very fast. And if you design systems for performance that may use the enablers of autonomy, you find that you can actually achieve the customer's goals much faster and more elegantly. So moving on to slide 10, analyzing autonomy. We are going to be introducing the frameworks that Lockheed Martin came up with. We'll do a quick overview on this now, and then we'll move on and kind of show these in context. So breaking down, looks like we have a slight formatting change from the transition, so bear with me on that. The operational framework is a visual representation of the system and how it's organized. This framework was established as kind of a critical enabler because vice the hand waving and the talking about things, you can actually use it kind of like an organic chemistry side of breakdown. What are we actually talking about? Where is the human? Where is the system? Who is the system talking to? What sort of interactions needs to happen? And on top of that, we're going to move over to the right side here, the autonomy behavior characteristics. These are basically how the system is going to behave. So planning and control, contingency management, system adaptation, things of those natures describe the interrelationships between the operational configurations and the entities in there. The trust framework in the middle here is critically important. Trust is a perennial problem within the design space of autonomous systems. And when we talk about things like the ethics of AI, where does ethics play a role in here? We'll get into that in a moment. And what this does is this starts to bracket trade space to be able to identify what the customer is going to allow the system to do. The environmental framework looks at what sort of considerations for the operational aspect of that. The environmental framework is designed to identify early the inherent complexity of an operating environment towards the problem of autonomy. For example, an air flight, blue sky, daytime, UAS is much simpler, and we see this with the DJI drones and everything else that we've got out there on the market, versus all-weather, nighttime, ground-based navigation. It's a much more complicated problem space when it comes to autonomy. And then the Root Autonomous Capabilities Framework takes the step from architecture into systems engineering, and it describes how the system functions. It breaks it down one step further. Now, for the sake of the conversation that we're going to have, we're going to leave it to the first 4 that I introduced. The racks are going to be part of a follow-on conversation, more tied deeper into systems engineering. We're going to focus a bit more on architecture with these frameworks. Moving on. So we had talked about the autonomy behavior characteristics on slide 11. We're going to see those autonomy behavior characteristics applied to those 3 dimensions in a MUM-T ecosystem. So a little background here. Under systems intelligence, our autonomy behavior characteristics build up with situation understanding, planning and control, contingency management, up to system adaptation. And the logic flow is as such. I can have situation understanding by itself. But to have planning and control, I must have or inherit situation understanding. Contingency management, by definition, is a deviation from a plan. And system adaptation is where I continue to execute contingencies vice the original plan, and I'm able to adapt my planning mechanisms or my situation understanding mechanisms to adapt my system so that my planning control is more robust. So that's on that vertical axis is situation understanding, planning and control, contingency management to system adaptation as a measure of intelligence. Across the independent operation axis, you see the autonomy maturity level. Now, these are going to be detailed, as Brian mentioned at the beginning, in the article that is going to be published in a couple weeks. There's a lot more detail that goes into that about what explicitly these levels represent. They are tied to industry standards and the latest academic literature on that. And then that Z-axis for system collaboration looks at the interaction between these. So multi-system operation, human system interaction, and human machine cooperation. So the MUM-T aspect of this and why this is so important. So I can have a sensor, let's say a satellite sensor, that can achieve a degree of situation understanding. It can be highly independent, but it's a lower intelligence, and it has a collaborative function between that and a planning and control system. Think about that on an F-35, maybe like an air battle management system. This would be smarter, probably has some AI in it, identifies and deconflicts and takes all this information and puts it into a good plan. We can then send that plan onto a weapon system, let's say a cruise missile, launch that cruise missile, goes flying into the objective. I don't need that cruise missile, that entity, to have all the situation understanding or all the planning and control, because I recognize that that entity is part of an integrated system. So it can inherit the planning and control and can be allowed contingency management. Now, as you cycle this back and you get feedback loops, whether that be the sensor actually visualizing that this cruise missile took a contingency or not, or performed as well as it did or not, or whether this system actually feeds back, can achieve system adaptation for the entire system. As you can see from here on the other side, the human system interaction, human machine cooperation, those are represented by the interactions within these subsystems, as well as with the pilot that might be in that aircraft. So this kind of helps break down this problem space and be able to articulate that I don't need to achieve the performance I want of that weapon system, for instance, I don't need to have that pegged full autonomy, full intelligence, full independence. I can actually balance this down intelligently to a systems of systems perspective. So with that in mind, we're going to start talking about designing for autonomy. So we've got the 5 frameworks, or we'll actually talk about 4 of those in context with this. Those 4 explicit frameworks are how we can begin to break down and analyze for autonomy, and that allows us to begin designing for autonomy. So autonomy introduces 5 major challenges for design. Defining the requirements, which is kind of the focus of a team that I worked with. impact of systems design. What are the complexities that you are going to identify or potentially unintentionally design into your system? And then coming out on the V&V side, your infinite state space, guaranteeing of safety, and then non-deterministic responses in its evaluation. So my slides, if I pause, my slide kind of goes blank for a second, so bear with me on that. So Lockheed Martin had focused 4 research areas on this. The MUMT IPT, the Manned-Unmanned Teaming IPT, is what myself and the other listed members at the title slide participated in extensively. They also kicked off a modeling and simulation team, a methods of V&V team, and a systems engineering lifecycle team. Now, we are in the process of fusing these together into a holistic SEIT kind of process, because what we found, our collective conclusion on that, was that autonomy's impact to the SEIT lifecycle requires initial considerations for all lifecycle phases to be moved before system design. And you'll see how that manifests itself in the next slide. So taking those frameworks and putting them into context, this is kind of where the rubber meets the road. So starting off with the custom requirements and going back to that kind of that waterfall chart, which I drew your attention to, is the customer requirements isn't always for that autonomy. It's for systems performance, for capabilities, for cost, it's for different things like that that need to be teased out. So classic kind of OR, mission analysis sort of thing, teasing out those custom requirements. Then you take those requirements, or we take those requirements, and we run them through the environmental framework. As I mentioned, the environmental framework's goal is to extract and identify complexity. Is it blue sky, daytime, air flight, or is it nighttime, all-weather ground activity? And that complexity then can go back and immediately, sitting down with the customer requirements with the environmental framework, we can negotiate whether this is going to be too complex or not. One of the key powers of this is you can also come up with phased, let's say, roadmap approaches to that. We've done this recently with a DARPA project. They're asking for a system that is very complex in the environmental scape, and they're held to those requirements. That's what they're looking for. But instead of trying to design that complexity in the extreme, we've provided the capability for a roadmap. How are we going to get there? So can we do flat terrain, daytime, fast driving? Yes. Okay. Well, we've got that checkbox. Now, what's the next phase for that? So teasing out the complexity so you're not getting bogged down with a million variables. You can start to almost break it into design of experiments of how you're going to phase that in. Now, one of the most important frameworks in this space to bracket the other side of your design space is trust. Trust is a function of ethics and assurance. What am I allowed to do, like legally or culturally, and how can I assure you that it's going to be performed that way? We're still developing the trust framework a bit more as we go, but the point here is taking what the customer asks it to do against the complexity of the environment in which it's expected to work, and then against what they will allow it to do. And so this goes 2 ways. The trust framework is very powerful in this aspect, because there are times where we don't, the customer will say, I won't allow a weapon or a system to do this. And you're like, well, hold on a second. We actually have history. We can test that. We've got security on that. It doesn't violate any rules, and it's not culturally infeasible. And we also have examples of where you accept this in the past. So are you artificially limiting yourself? On the flip side, we can do it the other way. The customer comes down, has this crazy requirement in a complex ecosystem, when we can come down and say, okay, you're actually violating one of your rules of ethics, and let's say it's a kill decision for an autonomous vehicle, for our sake at Lockheed Martin as a defense contractor. But then even worse, in assurance, you can't test it. And you're so integrated with other things that you have massive amounts of security vulnerabilities that are going to reduce or potentially torpedo your trust. So the whole point of this cone shape here, this funnel, is to bracket the design space and then give you fast frameworks to go back to the customer and say, hey, this is what you said. this is the complexity, or this is the barrier, or this is the enabler, however you want to look at it, and negotiate those down to reduce the complexity. At that point in time, we can look at the operational framework. How are these, once we get the requirements in the environment with the trust, we can say, how do we want these things to interact in a MUM-T environment? And it might be what we think about as a discrete system, except that discrete system is never purely autonomous. It's going to have interactions with the people and the other systems around it. Once we understand, let's say, the operational framework, how it's going to be, how it interacts and how that looks, that's the point in time at which we apply the autonomous behavior characteristics. This is the first look at truly the levels and types of autonomy that you would apply. And then that goes one level further down into the root autonomous capabilities, which really breaks down in the systems, the deeper systems engineering, let's say your detailed design area, where you could say that this is the kind of the what, and the RACS is the how you're actually going to achieve that. So one of the biggest benefits for this this operational framework is the ability to go from the macro view down to the system level view, and the ability to measure remote piloted sorts of things to autonomously piloted to swarms and to different MUM-T configurations. This dynamic and agile approach where you can literally trade this, where this, number 6 represents an autonomy behavior characteristic. Would I be able to achieve that with a 5? So that's a level that we would have associated with it. So the higher the number, the more complex or lower TRL, let's say, the enabling technology might be. But we can start to trade back and forth. How much autonomy do I actually need between these things if I'm going to achieve the actual customer requirements? And then break that down in the systems level view. This goes into digital engineering, where I can take the operational framework and hand it off to some of my modeling and simulation team. In this case, the images of AFSIM. And because we understand that autonomy is on those 3 dimensions, as is almost every other entity in AFSIM, of intelligence, independence, and collaboration, and the operational framework identifies the interactions and the levels of intelligence that are going to be required, I can quickly go in and test the design in a modeling simulation space and determine military utility or any form of utility or effectiveness of that to a decent degree for this initial design space. One of the projects that we worked as part of this research was doing what's called a value-focused thinking activity, pioneered by Parnell, and back in the late 90s. It's a very powerful tool that helps you identify value and impact. So what we've done is we've taken bins of hundreds of enabling technologies and binned them by value score against the autonomy behavior characteristics and relative TRL level. What this allows us to do quickly is look at, bracketing long-term investments versus short-term investments versus challenging investments. For instance, and I don't think you'll be able to see this, but this here that I guess you can't see where I'm circling. In challenging investments, there's one that's called gesture recognition. Well, you may have a customer that comes down and says, I would like to have a UGV that can look at a Marine and recognize arm and hand signals. Well, very quickly, we can come down and look at this and say, well, that's a challenging investment. That's actually very difficult to do. So breaking that back out, what is it that you're actually trying to achieve by asking for gesture recognition? And more importantly, can that goal be achieved with a less complicated and less challenging technology that might be in the short-term investment, or it might be the partnering of a couple different technologies that we hadn't thought of before? But what it does is it takes something that sounds good to begin with, that custom requirement, breaks it all the way down into the enabling technology and starts to identify additional complexities, in this case, investment complexities or TRL level challenges that exist on that. And as we go, I think one of the most important aspects of this is not a waterfall. This is more applicable to things like, Will Roper talks about his holy trinity of acquisition, agile development, digital engineering, and modular systems. So what you've kind of seen in here in this aspect is digital engineering we saw with the ability to do the modeling simulation. What I should have mentioned back there is we have the ability to take the operational framework and convert it immediately into SysML language so that we can start to do classic systems modeling, entity or state diagrams, state modeling and things of that nature. But then, so we've got the digital engineering aspect, we've got the agile, where this is intended to be iterative. If you come all the way from customer requirements down to an architecture before you ever bounce back up, you probably have ingested way too much complexity. The idea here is coming from customer requirements to environment, coming back up and clarifying, coming across to your trust, identifying that, bringing it back up to the requirements and deconflicting, bringing it down to the operational, taking that operational framework, putting it in the SysML in the digital engineering world, putting it into modeling and simulation, testing it, testing feasibility, testing effectiveness, testing utility, going down, clarifying the autonomy behavior characteristics so you can further reduce and trade complexity, and then getting down into that systems architecture. And then even iterating on that as well, so that kind of agile development. One of the Trinity of Roper's was modular systems. And I think the operational framework nails that one, where you can see how these entities can start being traded back and forth within a modular kind of construct. And so as we come down and out of the design space, what we've identified is with the requirements analysis supported by the environmental and trust frameworks, with the operational framework, we can achieve definitive improvements in defining the requirements and understanding the impact of systems design. By looking at the testability or the complexities that are inherent at the environmental and the trust stage, we're already front-loading the risks of infinite state space and non-deterministic responses in our V&V. And then designing for balancing these levels as we go down really nails the last three completely. So achieving, reducing the opportunity to find yourself in infinite state space, the ability to ensure safety back with that trust and the ties and the teaming, and then the evaluation of the non-deterministic responses, or even if possible, reducing those. So non-deterministic responses, talking about trade space, non-deterministic responses become a problem if it's on an entity making a final decision. But non-deterministic responses are actually very acceptable within planning and control functions in a human in the loop sort of function. So think of an AI-enabled battle management system, goes through the non-deterministic stuff, the human looks at the output, selects the appropriate course of action, hits go. We're much more okay with that non-deterministic response than we would be if it was on the final engagement asset. So wrapping up, and I think this is my final slide, we are able to then, with these frameworks, align from the customer needs, doing those requirements analysis, understanding the performance, the cost, the TTPs, what the customer is asking for beyond autonomy, identifying that architecture, architecting to maximize the value, model that performance, and define those relationships, at which point in time we apply the autonomy determinations using the autonomous behavior capabilities framework, and identifying the gradient of how it is going to be achieved, the trade space, and then identifying the enabling technology. And as we get down the enabling technology, it's balancing solution TRL, really capturing your discriminators and informing future investments. And this feeds up and back down in this space. So that wraps up this presentation. Again, there's a lot more supporting material. The levels are clearly articulated in the paper that's going to be published in a couple of weeks, and all the source material for what we were able to come up with. So pending any questions.
Great, thank you, Michael. Wonderful presentation. I appreciate the pretty succinct and obviously well practiced. So that was great. we had to get a couple questions that came through in the Q&A portion, so I'll kind of work through those. Again, if anyone has any questions, please submit them that way. A couple more did come through chat, so I'll sort of weave them in as well. So let's see. I'll go ahead and just put them on the screen. So you should be able to see this as well as I, Michael. Is that correct?
Again.
Okay, so here we go. Autonomous systems require sensors, cameras, LiDAR. How do you ensure system performance under adverse weather environments and/or enemy attacks, obstructing vision?
That's a great question. This is one of the interesting aspects that we found within the trade space, and I'm going to add in a new term that I've used in the cybersphere. So we talk about systems, and we talk about them being like resilient and hopefully maturing into anti-fragile. One of the problems is, so the sensor systems, if you have a system which is relying completely on a sensor, and that sensor gets taken out, that's why that looking at the MUM-T ecosystem, where you look at the 3 dimensions of autonomy, if your situation understanding gets truncated through your sensor feeds, and you are unable then to do your plan and control or contingency management, and you have a threat, going back to the security layer, you have a threat that may break that link. You have what I call a fragile system. So when you find that sort of security risk in your sensing systems and the ability to continue their mission, that's a great spot to look for either the resiliency and or what I'll borrowing from Nassim Taleb, anti-fragile. So how do we, in that teaming MUM-T environment, realizing that I don't just have the discrete system, but possibly an integrated system, how can I overcome a security risk of a sensor into my autonomous system? So the answer isn't explicit. The answer is more of why we develop these frameworks, to be able to kind of work with these trade considerations and identify the risks, which is why we added that security layer to how we analyze for autonomy, is this exact sort of a problem set. So I hope that answered the question.
Yeah, no, I thought that was great. Fortunately, the attendees can't respond back, but I think that was a great answer to it. Thank you. All right, let's see. Next question. Go. How does system safety play into the trust framework, or does it? And if it doesn't, where do safety considerations come into play?
Great question. Actually, a really good question. So right now we have culture, rules, testing, history, and security as part of the trust framework. But that's actually an exceptionally good point. Where does safety work into that? And like I said, the trust framework is still in process, so I think you've given me an aha moment on that one, that we haven't necessarily articulated that explicitly. I would say that is a key function. You would probably have that under assurance, because we talked about trust being a function of ethics and assurance. And I would say the assurance of safety, along with security, is a very important aspect of that. So very outstanding question on that one. I appreciate that. So that's where I would consider it would be under that trust function. Yes.
Okay. Another one. Interesting question here, but how useful is history in evaluating the ethical considerations when posed against a constantly evolving geopolitical environment where our adversaries are not bound by the same ethical considerations? And does that end up hindering our ability to provide tactical overmatch against our adversaries' capabilities?
I'd say very, very, very useful. And I think there's 2 considerations on there, because we capture history. Now, history, as I've articulated it, is more the history of the actual asset. For example, let's say LiDAR technology on a self-driving car has a long and proven history that we can leverage for assurance. But in your case, you're talking about more, not on the line of assurance, you're talking the history more on the line of ethics. And so ethics, we talk about culture and we talk about rules. So those 2 are not always in sync. So for example, your culture can find something permissive, let's just say the use of cannabis products, whereas the federal rule is still against that. And so eventually what you're seeing is that cultural implication is slowly eroding that rule away over time. It may snap back, it may change, but those two are in balance. So history is important. Now, I think what you've hit on, which is why when we design our frameworks, we try to do this so you could model both a human or a non-human with any of these frameworks. So for that instance, I'd say that question of history falls into the cultural implications, because no matter what it is, so I'm former Army, deployed to Iraq, and your question about hindering our overmatch. Well, our rules of engagement to a lot of people felt like it was hindering our overmatch. The problem was, if we played by their rules, we would be violating our own cultural ethics. And so there's a balance point in there where I don't believe that the ethical considerations, that's a dangerous thing when we talk about, just warfare theory or things of that nature. I think where you balance that in is in that trust framework, really identifying those considerations. And something that we may actually culturally find acceptable, let's say a killer robot on the battlefield, our enemy may find to be absolutely morally abhorrent, which could create its own backlash. So these are the considerations that we get into in that trust framework.
Oh, that's great. And we got another question that came in that just generally asked if you could speak to or elaborate more on the ethics side of autonomy. So I think you sufficiently hit on that question as well. So kill two birds with one stone there. Okay, next question here. Are these frameworks available for the DoD organizations to evaluate and assess how they can be used within our specific problem space? How would we go about requesting access to these frameworks?
The simple answer is yes, and I think that would be reaching out to myself, and I think we'll be able to provide our contact information, reach out to our OA team who performs that, and we can start to talk about that. So given that we're a DoD contractor, we can support all levels of DoD design, ideation, and analysis. And so, like I said, the majority of this information is going to be actually published in the DSIAC journal in 2 weeks, which will give you a good access. And then we do stand ready to support with the full details of those frameworks as we go forward.
Okay. Yep. Perfect. Right. And I don't think your contact information is immediately available on any of the DSIAC web pages or anything right now. So we will either, if I'll talk to you maybe offline about it, but with your permission, we'll include it in the follow-up email that we'll send to all the attendees, and or they can always just contact DSIAC, and I'll get them in touch with you. That should work.
I just dropped my email in the attendee chat if anybody wanted to reach out immediately.
Perfect. Okay, next question here. What are your thoughts on building assurance arguments for autonomous systems?
That's a difficult. Gabor, can you chat a clarification on that one?
Yeah.
Or you can speak if you have the microphone on.
We could hold off and come back to that one. Maybe if Gabor wants to type it into the chat for a little bit of clarification, we can come back to it. So let's
okay. So I'm wondering if I've answered that one in part for the question, sure. And I'm not sure exactly what's being referenced by assurance arguments. I'll give you an example of how I interpret the question in case this helps. Is that a lot of times, I kind of mentioned this before, but somebody will say, "Hey, I don't, let's just say the contractor is proposing a solution to the DoD, and the DoD says, no, there's no way we'll accept that. I can't trust that." Well, one of the ways you can make an assurance argument on that is to say, hey, look, we can test it to the high fidelity that you're asking for. We've got history on this. So a great example for, let's say, autonomous decisions for final engagement of a target. When we launch a HARM missile, anti-radiation missile, we give it basically EM signatures to look for, and then we release it. And when it finds one of those EM signatures that meets the profile and other considerations, it engages the target. So using that history that we already have, that would be an argument for assurance, along with then the security features. And I'm not sure if I met your expectations for assurance arguments on that. Oh, assurance cases?
There you go. Yep, saw that too.
Clarified by David. Okay, there we go. Okay, thank you. Assurance argument explains the system is safe even if some parts are not working correctly. Perfect question. That actually is a great consideration. I'd say that's actually not actually explicitly addressed in the trust framework. That would be something I would address more in the operational framework, and then the ABCs and further down to the racks. That gets in from your fragile towards your anti-fragile, about showing that kind of gets into classic, redundancy or something that I call in anti-fragile land graceful degradation. How does the system recognize that you've got an issue, and then how does it react with that? Can it continue? Are there known parameters? How does it manage that? That's something that is a good consideration up front. I think that one is actually better addressed further into your detailed design in systems engineering, and then your what's the term I'm looking for? Kind of like your resiliency functions.
Good. No, that's good. I think that certainly addressed that one, so that I appreciate the clarification as well. It's helpful. All right. Next question here. Is the format and structure of the operational framework structure based on an existing standard and language? Makes sense of that.
So that's a good question. So the operational framework came after our original autonomous behavior characteristics framework. The ABCs are taxonomic framework. Those are based on academic literature and the use of the terms as used by the industry. You'll see that defined much more explicitly in the paper on how those are derived. So the operational framework is more taking the considerations and using just like, where's my human, where's these different things, and placing them into the relationship mapping, and then applying those ABCs, which are built on an existing standard and language in that sense. The question from David Chamberlain.
Mm-hmm. Got it. Let's jump to the next one here. Do you have any guidelines on division of labor / responsibility for autonomous entity versus human, aside from non-deterministically modeled scenarios?
Yeah, that's another good question. Okay, guidelines. So what we talked about with the frameworks is identifying complexity, balancing out your system design, preferably and more aptly, probably actually ironically, reducing the amount of autonomy that we're expecting of these things, right? So what you find out is there's a lot more just good natural teaming opportunity versus handing it off. So a great example of this, and so I don't have, my guidelines would be going back to what we talked about is balancing the TRL levels, balancing, MRL. I saw it up here, the conversation of integration readiness levels. Yes, these all come into play when it comes to this. So it's all part of that balancing act, and I don't think there's an explicit guideline. It really depends on what is going to give you maximal utility with reduced complexity, so that you can actually design and deliver a system that can be used. So the guideline would be keep it simple, stupid. In the old KISS, systems engineering, Axiom 101, is just balancing that out and trying to figure it. And so I would say, yeah, avoid your non-deterministically modeled scenarios, find the things that you can V and V, and then there's actually a little aside, an interesting twist is you've got to get into cognitive science for this. Because things like the cognitive bias codec, which you can just Google cognitive bias codec, there's 180 named biases broken into 4 categories. And the problem that we have is AI can help enable human decision making, but humans are exceptionally good at the final decision. AI is exceptionally good at data aggregation. So if you compare those two together, humans do make really good decisions, actually based off smaller data sets. You give a human 10 or 100 data points, they make good decisions. You give them 10,000 data points, they inevitably apply more than one bias to it, and you find yourself in an edge case. Now that's a different conversation on AI and human engagement.
That's good. No, I appreciate that. And like you mentioned, you kind of addressed the other question that was asked a minute ago about IRL anyway. All right. Next question. When the autonomous system is distributed, such as a swarm of UAVs, what type of systems principles will be more important? Perhaps important for the successful autonomy?
I say I'm gonna pick on your word swarm because I think this is the first important systems principle. Are we talking a tactical swarm or a perceptual swarm? And it's a funny question because you can actually achieve a perceptual swarm, that is the mass overmatch of an enemy's defensive capabilities, without actually having to have a single inbound asset collaborate. It can all be done through high fidelity integrated systems, mission planning, things of that nature, using very unintelligent final actors. So that would be my first question when you talk about systems principle for successful autonomy in swarms. Do I even need it, or can I achieve it offline back in the mission planning where I can actually apply non-deterministic AI because it's not making kill decisions because a human approves every single one of those mission plans, but can achieve a swarm perspective or perception. Now, if we're talking swarming as in the interoperability and the ties, it all goes back to how do you balance the communication needs, how much a prior information, all these other things. So going back and looking at it, the first one is challenging. What are we even talking about for a swarm for the customer need? Do I need to have really smart assets engaging, or can I achieve that with something else? That would be my first design principle for successful autonomy in something like a swarm.
Well, that's great. That's a great point. I mean, you don't want to just incorporate swarms unless there's a need for it. All right, next question, and I do want to just pause and apologize. There are some questions that were asked in the chat that I've kind of got saved on the side that after we get through these other questions that were submitted. Though I will note that given our time constraint or the time we're getting at here and the amount of questions are in queue, we might not be able to get to those that were asked in the chat. But we'll do our best here. So here's the next question up. Yeah, so you mentioned earlier in the presentation the example of long-range fires when talking about the challenges in identifying a uniquely MUM-T solution to a customer need. Can you provide a good example of such a need?
Yeah, let me think on this for just a second.
Sure.
About the challenges in identifying uniquely. All right, so I'd say a great example that I'm actually working with explicitly is the air-launched effects under the A-Team project within the Army. So one of the things that we've been working with the design team is trying to understand what is the actual need. So first off, with the mission analysis, what was interesting with the ALE is, this might be just a Lockheed focus, but it was on IADS disintegration. Well, the problem with an air-launched effect is it supports an Apache or the new FARA aircraft. And the consequence of such suggesting that the FARA or the Apache are going to go to IADS disintegration is that it's not actually in their mission space. So if we focus on a solution that only goes after IADS disintegration, it misses the fact that the Apache and the FARA actually have existing mission sets that aren't IADS disintegration. In fact, I used to be a fire support officer for an Apache unit. I would, as a fire support officer, run seed and deed missions, eliminate the threat, and then bring the Apaches in to mop up afterwards. So the first question on that is, why are we trying to go after that mission? Because that's a wickedly complex mission for autonomous systems. Once you can peel that back, then you look at the implications for the other considerations of those mission sets. So for instance, do I need to have everything be highly collaborative or everything else? Well, if I just need to get sensor extension, what if I just send a very low cost, very fast, really dumb synthetic aperture radar to go flying around that hill mass, scan through and pick up things, come back, and because it might be C2 denied, I don't have to have it report the entire way. It just boomerangs around the hill, comes back and at close range to me can dump the data and update my common operating picture. So that's kind of one of those things that when I look at this is trying to deconflict. First off, I don't need to have all these super smart systems flying out there to do it. I can actually start to layer and trade on this by looking at what the actual needs are going to be. And I apologize, I'm going to cut that answer short because we are at the top of the hour in case Brian needed to do anything to close out.
Yeah, no, that's okay. I mean, as long as you're okay hanging in, we'll maybe do a few more questions till about 1:05 here, since I kind of stole about 5 minutes in the beginning of the presentation. So if you're okay with that, we'll proceed with just a few more.
Yeah, and so let me for the Alfredo question on the uniquely MUM-T solution. So the interesting balance of that is also from a MUM-T perspective. It's not that I need an air-launched effect, an autonomous asset to go and do all these things. I really need to get in the brain of the pilot and find out what does the pilot need from that. And if not the pilot, what about the ground commander? What about the different levels of humans that are engaged with that? So I think that kind of puts the bow on your question of the unique MUM-T considerations, is both balancing the solution set for what they actually need to balance complexity versus simplicity, and then understanding the need from mission analysis and from multiple different perspectives.
And then just to be clear, you're okay proceeding to a few more questions here?
Yeah, I can take a couple more.
Yep. So maybe 1:05 here. All right. So for M&S, what are your thoughts on modeling performance of an autonomous MUM-T system or autonomous/MUM-T system versus a human adversary? The challenge of human adversaries are the unknowns they can introduce, but the model of that adversary is not going to have those unknowns.
You hit it on the head. That was the kind of an aha moment, kind of beating my face against the wall. How do I model improved autonomy performance? You know, how do I model these different behaviors? Well, holy cow, we already only model, air quotes, autonomous systems in a M&S environment because there's no humans in the M&S environment. So to your point, if I'm making a proxy of a human and a proxy and an autonomous entity, let's just I put an AI algorithm in there of some nature, well, that proxy of the human is only as intelligent as I do it. So Lockheed's working on something we call an AI engine. It works in a 6DOF simulation, working in AFSIM in a 3DOF mission model. And so what we can start to do is kind of play AI against AI to try to get what you're asking for, those unknowns, against your own proven algorithm. The other aspect of this, I'll borrow this from cyber modeling and simulation and wargaming, is that certain aspects of like cyberspace are really good for modeling and simulation, but others aren't, like human reactions, functions like that, which require wargaming. So one of the things I would recommend is it's not only modeling simulation. It's probably modeling and simulation with a function of wargaming, where you might have iterative stops where decision comes up, a human on the other side who's red team can make a decision that can throw you those unknowns.
Mm-hmm. Yeah, that's good. Okay, time-wise, this probably will be the last question. So, see how nice this is. Has the framework been assessed for when technologies are asked to be commonized, even when platforms don't share missions? That is, say, what if one system is more complex and its core technologies are leveraged on simpler systems? Is there a sub-iteration in the framework?
I don't see the need for the sub-iteration of the framework because the ABCs already start to identify some of those. And then what you're talking about is maybe you're just getting reuse of it. So if I'm understanding the question right, if I take a complex module and I put it into a simpler system, well, now what you're just talking about is kind of a cost risk, because I may not, like let's say I have a gaming laptop and I use it to surf the internet. I'm not using the gaming laptop to the full capabilities of what it can do. Doesn't mean it's not useful, but it's probably a lot more expensive than I really need if I just want to look at Facebook. So when you look at the commonized aspects, I would actually invert it, and I would say the commonized aspects probably have, these frameworks work best when the commonized aspects are actually lesser intelligent, meaning, going back to kind of the ALE example, what are the less intelligent capabilities that I could actually pair together? So take modular open systems architecture sort of construct. And if I have 3 subsystems and each one has a kind of capability, can I just pluck those out, plunk them together, put some glue between them, and actually achieve a more intelligent capability through that MOSA architecture? So that is where I see the value of those frameworks in some ways, is to actually do the inverse, taking lesser intelligent aspects in those TRL balancing and putting them together to achieve something greater.
Perfect. Yeah, that's great. All right. Well, hey, there are some other questions that were asked. We're gonna retain them. You know, I'll share them over with Michael. We can decide what we want to do with them. But if there are any further questions that you really are like to get answered, aside from, of course, trying to contact Michael, you can ask DSIAC. We'd be happy to entertain your questions, and some of our staff could help try to answer them as well. But otherwise, I do very much appreciate everyone joining in, sticking with us throughout this. The question and answer, I think, was really valuable time we've spent here. And Michael, thanks so much for fielding all of them, responding to them so quickly, and of course for your presentation.
Yeah, absolutely. Looking forward to it. And like I said, I put my email in the chat if people saw that. Feel free to reach out to me. Otherwise, I think Brian's going to put it into a follow-up email. I appreciated the questions. Those were very good. Thank you, and thank you for your time.
All right, we'll end it from here. Thank you all.